All right, welcome to physics. We're going to be taking a quiz in just a minute. And by the way, I want you to get in the habit of doing that. I may not do it every single day, but most days that is definitely what I'm going to do. We're going to start the day with a quiz. It'll be on Canvas and it'll be locked. If any of you have tried to get into the quiz, you've noticed that it's locked. And it'll be locked for about 1 more minute, and it'll unlock in a minute. And so then take the quiz. Now, I am limiting you to 5 minutes, and some of the people in the earlier class this morning, they said that they didn't think 5 minutes was enough. I'm still going to limit it to 5 minutes. If you don't finish it in 5 minutes, don't sweat it, because you are allowed to retake it. Now, I'm going to keep it locked until tomorrow afternoon, because I need to go in and I need to see how you guys did on your first attempt. I need to know what are some things that you're strong at, what are some things you're weak at. So I need to see your first attempt. So I'm going to keep it locked until tomorrow afternoon, and then I will unlock it so you can then go back and retake it if you want. So don't fret too much if you don't get a great score. And yes, I did unlock the old one. So you can go ahead and you can take that. All right, so it is now time. The quiz should now be unlocked, or at least, for your first attempt. All right, so go on to Canvas, look for the quiz that's labeled Quiz 2B. Once you start it, Canvas will start a 5-minute clock, and then it will automatically submit it at the end of 5 minutes, whether you're done or not. And like I say, don't sweat it if you're not done. Okay, I'll see you guys in about 5 or 6 minutes then. And I'm going to pause the recording because there's no sense in letting that keep on going while nothing's happening. Okay, I'm looking right now, seeing that everybody's finished except for one person who joined a little bit late. That's okay. So let's go ahead and start talking. So first off, when I look at your scores on this quiz that you just took, what I see is that some of you finished the quiz really quickly. Some of you only took 3 minutes to do the quiz. But the people who finished the quiz really quickly did not get the highest scores in the class. Please, guys, understand that the goal here is not to be the first one done. The goal is to get the highest score that you can possibly get. So I'd recommend that next time, instead of rushing through it and trying to finish up in 3 minutes, take the full time, give it your best shot. Now, although I do see a few good scores in there, I also see a fair number that were not. So Jackson wants to know what's the answer to the last question. I'm not going to answer that, Jackson, because tomorrow afternoon, when I unlock the quiz and I let you guys go back and retake it, it's going to be the same question. Ideally, what I would do is I would have the quiz retake be different questions, but teaching online is so incredibly time intensive. I just do not have the time to make up multiple quizzes. So I'm not going to tell you. And everybody hopefully understands that the score that you get on the quiz just now is really more for my benefit than yours. It helps me to understand what are the things that you're good at and what are the things that you need a little more work at. And I need to see what is your first score, not the score after you've retaken it 4 or 5 times. Tomorrow afternoon, when I unlock it, go back in, retake it, and get the better scores. Just remember that when you retake a quiz, you have to tell me that you've retaken it, because otherwise it will not automatically get updated. I don't have Canvas and Aspire automatically connected together like some of your teachers do. Okay, so let's see, good. Okay, so everybody's done now. All right, let's talk about last night's homework. Here are the answers to the ones that there aren't answers for in the back. So I'm trusting you've already looked up the ones that have answers in the back. Let me give you a couple minutes to look those over. And if anybody has any questions, now's the time to ask. I do not have time in class here to talk about all of them, but if you want to talk about 2 or 3 of them, that'll be okay with me. And you can see that number 28, 32, and 33, those are ones that I want to discuss. So I'll hold off on those for right now. I'm not seeing any questions in the chat box. I'm not hearing any questions. Okay, so I see a question saying, is it bad if you said 20 meters per hour for number 26? Well, if it works out to be the same number. Uh, Sometimes they ask you to give the answer in certain units and other times they don't. So as long as 20 meters per hour is the same as 0.33 meters per second, I'm okay with it. Right? Not hearing any questions other than that. All right, we'll tell you what then, let's discuss the ones that I want to discuss. So number 28 is an important one to discuss. All right, so on number 28, they're saying that we're taking, or this person is taking the dog for a walk and she's moving at a constant rate. Okay, so if we were to do a motion diagram, which is also sometimes called a dot diagram, what you should see is the dots should all be evenly spaced. Whereas if it was a position versus time graph, so position versus time, what you should see is it's a straight line, okay? And then if we really want to do it right, which we probably should, we should make sure that the slope of that line is the point, whatever number that is. I can't read without my glasses here. So 0.55. So we should make sure that the slope is 0.55 if we really want to do it right. Okay, so that one pretty straightforward, I hope. Number 32 is one I wanted to discuss. On number 32, they were asking, how are average speed and average velocity related to each other? Could one of you unmute yourself and tell what is the similarity between the speed and velocity and what is the difference between them? So Adam, these are questions from chapter 2. Look up at the top of the page there, see where it says 2b. The 2 means chapter 2. Okay, so who is going to tell us velocity and speed? How are they similar? How are they different?
So like speed is like total distance divided by total time. But then like velocity is like displacement over like total time, correct?
Okay, very good. That's a true statement. And if you are only traveling in one direction and you never turned around and went backwards, or you never turned right or turned left, what's going to happen is the magnitude of your velocity will be equal to your speed. But if at any time you turned around and went a different direction, then the magnitude of your velocity will not be the same as the magnitude of your speed, at least not the average velocity. Now, the instantaneous velocity and the instantaneous speed, for those, the magnitude of the instantaneous velocity will always be the instantaneous speed. But if we're talking averages, then the average velocity, the magnitude of the average velocity will only be the same as your speed, your average speed, if you only went in one direction and at no point did you ever turn around or turn right or turn left. So Taituan just typed something in the book, or into the chat box. He says, in the book, the average speed is the average value of the average velocity, or the absolute value of the average velocity. That is true if you never change direction. Well, if you went one direction and you kept on going that one direction, then what you just said there, Taituan, is true. But if at any time you turned around and went the other direction, then the magnitude of the average velocity will not be the same as the magnitude of your average speed. Okay, and then the last one is 33. So why is it important to always draw a picture? All right, this is something that I am going to really stress because I think it's important. On all these problems here, if you've got some object here and it moves this way for a while and then it turns around and moves the other way for a while, don't just try to do it in your head. Draw it out. You know, like for instance, on this extra problem here, right? We went this way for a while and then we turned around, we went that way. Draw it out. Draw a picture. The best thing that you can do to help understand physics problems is take the words that you've been given and draw a picture from those words. That is one of your best problem-solving strategies right there. Okay, any other questions before I move on? Going once, going twice, sold. Okay, I'm going to assume that you don't have any questions about the homework. Let's move on. We are going to start into chapter 3 today. Up until now, we have always assumed that whatever it is we were looking at was moving at a constant speed. But effective today, from now on, we're going to allow that maybe the thing is accelerating or decelerating. Okay, so acceleration is something that you need to understand. And I'm sure that most of you understand what acceleration is, but I also am sure that some of you don't. So let's talk about what is acceleration. So let's say you're watching TV or whatnot, and they come on with a advertisement for a new sports car. And they say that this new Lamborghini can go from 0 to 60 in 4.1 seconds. Well, what they've just told you is how quickly it can accelerate. Because any car can go from 0 to 60. I mean, heck, even a Volkswagen Beetle could go from 0 to 60. But a Volkswagen Beetle probably couldn't do it in 4.1 seconds. Okay? If you have a Volkswagen Beetle, it might take it 4.5 minutes. Okay, or hopefully not that much. But if you give it enough time, it can eventually get to 60. So the key thing for acceleration is not only do you need to know how much the velocity changed, but you also need to know how long it took to change that velocity. So I'm going to write an A here for acceleration, and then I'm going to write an equal sign with an extra line up above it. And we used this symbol last time, and boy, are we going to be using it a lot. Somebody tell me, what does it mean when there's an equal sign with an extra line above it? What does that mean?
It's defined by?
Is defined as. Okay, so acceleration is defined as the change in your velocity, which I'm going to write using this triangle symbol here. This is something that I hope that your math teachers have used. That delta, by the way, that's the Greek letter delta. Okay, that means what is your final velocity minus whatever was your initial velocity. And same thing with delta t, that means what is your final time minus whatever was your initial time. That's what delta means. So this is the definition of velocity. So if you started off at your initial velocity of 0 and you ended up at a final velocity of 60, and the time that you took was 3 seconds, so we're going to assume that the final time is 3 and that the initial time was 0. And you're going to find that we do that a lot. In many, if not most situations, we're going to assume that the initial time is 0. All right, so what is the acceleration of this sports car here? Well, 60 minus 0 is 60 divided by 3. So the answer then works out to be 20. 20 what? What units are we talking about? Well, it depends on what units we use for our velocity. So when we're talking about cars and they say 0 to 60, they're talking about miles per hour. Okay, and then, but the time is not measured in hours. The time was measured in seconds. So this gets really confusing. So the units here are going to be 20 miles per hour per second. So what that, oh, actually, how did we get 3 seconds? It was 4.5 before. Okay. Well, anyway, we changed it to 3. So we got an even better sports car now. It can go from 0 to 60 in 3 seconds rather than 4.5. Okay. So the acceleration then is 20, but the units are miles per hour per second. So what that means is when t equals 0. So here's the car here, the velocity equals 0. So then it starts moving. So 1 second later, let me erase this to make a little room here. Okay. So 1 second later, when t equals 1, it is now moving 20 miles per hour faster than it had been just 1 second earlier. So the velocity now is 20 miles per hour. 1 second later, t now equals 2, and notice the dots are getting farther apart here. So the velocity now is 20 miles per hour faster than it was before, so now it's up to 40 miles per hour. And then 1 second later, so now we have t equals 3 seconds. And again, every second that goes by, we just add 20 onto whatever our velocity was. So our velocity now is 20 greater than 40. So our velocity now is 60 miles per hour. Okay. So when we say that our acceleration is 20 miles per hour per second, don't forget to get the per second in there. That's important. That means that every second that goes by, our velocity increases by 20 miles per hour. Okay. Now, units like if we say that our acceleration is 20 miles per hour per second, that's kind of confusing. I mean, it is totally valid, but if you work in standard physics units, it makes a lot more sense. So instead of measuring speed in miles per hour, let's use standard physics units, which you guys are going to get really familiar with really quickly. Standard physics units for speed are meters per second, and the standard unit for time is always seconds. So if we were measuring things in meters per second instead of miles per hour, if we said that our acceleration is 20 meters per second, that means every second that goes by, our speed is 20 meters per second faster than it was the previous second. So it's going to go 0 and then 20 and then 40 and then 60. And so every second that goes by, our speed goes up by 20 meters per second. Now, don't be surprised if you see it written a different way. You're going to see it quite often written as 20 meters per second squared. And these two are the same. And it's important for you to understand why they are the same. So if we've got a fraction where we got basically a fraction inside a fraction here. What we've got is we got meters per second on top, and on the bottom we got seconds, which is the same thing as seconds over 1. So we've got a fraction inside a fraction, which can be confusing. I like to avoid having fractions inside fractions. It's kind of makes students' heads explode, which on the other hand, maybe that's a good thing. But let's see if we can take this fraction inside a fraction and change it. So what I'm going to do is I'm going to take the fraction that's on the bottom here, and I'm going to flip it, and then I'm going to multiply top and bottom by this same flip thing. So if I got seconds over 1 times 1 over seconds, that goes away. And so what I'm on top here is I've got meters times 1, and the bottom I got seconds per seconds. So you see how I got the units here? So if I say 20 meters per second, that is the same thing as saying 20 meters per second squared. Get used to that. You're going to see it both ways. And when I'm talking, sometimes I'm going to say 20 meters per second, and other times I'm going to say 20 meters per second squared. And so hopefully you guys are now comfortable with the idea that they mean the same thing. All right, any questions? Not hearing any, not seeing any, okay. Let's move on. All right, so what we want to do now is we want to show accelerated motion various ways. The first way that we learned how to show accelerated motion was with a velocity with a dot diagram. We did that first, which is called a motion diagram. All right, so if you're moving along at constant speed, The dots are all equally spaced. But now, all of a sudden, you step on the gas. Therefore, the dots start getting farther and further apart. Okay, that's how you show accelerated motion on a motion diagram, or also called a dot diagram. But the graph that I prefer is the position as a function of time graph. That's not supposed to be an F, that's supposed to be a T. Okay, all right. So during this first part here where we're traveling at constant speed, well, that's just going to be a straight line. And then during the second part where we're accelerating, what's going to happen is that it's going to be a curved line. So this is how we show it on a position versus time graph. We start off, if it's constant speed, it's a straight line. And as soon as we start accelerating, then it becomes a curved line. And now, what if we're slowing down instead of speeding up? Okay, what would that look like? Right, well, if we're moving at constant speed, that's still going to be a straight line. But now,
it would curve down.
Yeah, I think you're right there. So if what's happening is we're slowing down, so rather than drawing the dots there, I'm just going to say that we're slowing. Okay. Well, what's going to happen is the slope is going to get less and less and less, and maybe it'll eventually come out to be a horizontal line. Maybe not. Okay. But the important thing is that the slope is getting smaller. I mean, if you look at the slope at each one of these points, you'll see it's changing. It's getting slower. Right, so this is how you show it on a position versus time graph. Okay. Right. Now, let's use an elevator as an example of understanding how things are going. So here's a big building. Whoops. Okay, I forgot to turn on annotation. If I touch my screen without turning on annotation, then it does weird things there. Okay, so here's the ground floor. Here's a big tall building. All right, here's the elevator. And so somebody gets into the elevator. That's supposed to be a person. All right, so initially the velocity equals 0. So let's say the velocity equals 0. And then they push the button and the elevator starts moving up. So at first it's moving slowly and then it gets faster. And then here's a point where it's moving at constant velocity. All right, and then as it reaches the upper floor here, then it's going to start slowing down. And then here it finally comes to a stop. Right, so if I were to draw the velocity vector, well, at first there's no arrow to draw because the velocity is 0. Then the velocity starts getting bigger, velocity gets a lot bigger. Now the velocity continues on, so these two are the same because it's moving at constant velocity. Now the velocity arrow gets smaller and eventually comes back to a stop. All right, so those are the velocity vectors for this elevator. Now let me switch to a different color here. And now let's look at the acceleration. So I'm going to do the acceleration in red. So you see from this point to this point, the acceleration or the velocity was 0 and now it's bigger than it used to be. So that means my acceleration is in the upward direction. And here it's still getting bigger, so we're still accelerating. Now, this acceleration vector, let me get rid of that. So my acceleration vector right here might be the same as my acceleration vector there and might not. It doesn't, an elevator doesn't have to accelerate at the same rate, but most of the time they do. So let's assume that we're accelerating at a constant rate. Let's pick a number, like say maybe 2 meters per second, right? So during the first part of our trip here, the elevator is accelerating at a rate of 2 meters per second. But what's happening right here? Our velocity at these 2 points is the same. The velocity here and the velocity here are the same. So what is our acceleration then? So somebody either type into the chat box or unmute yourself. during this time right here, what's our acceleration? Okay, good. So our acceleration vector goes back to being just a dot because the acceleration vector is now 0. Now here's where it gets really interesting. So we, in between these two times right here, we had our velocity being a big number, and now our velocity is getting less. So what's our acceleration vector going to look like? Well, our acceleration is going to be negative because we are slowing down. So the acceleration is negative. So I show that as an arrow pointing downward. So notice, even though my velocity vector is still pointing in the upward direction, so the elevator is still moving upward, but because we're slowing down, we say that our acceleration vector is pointing the other way. So we decelerate here, which is just negative acceleration. Deceleration is just negative acceleration. Okay. So we started off with positive acceleration, then we went to 0 acceleration, and now, through the last part of the journey here, we have negative acceleration, which is also sometimes called deceleration. Okay. And then the same thing works the other way around. Let's say that the elevator is now moving down. So here's our building. Here's the elevator up at the top floor. So we get in the elevator and we push the down button. So initially our velocity is 0, but then we start moving downwards. So our velocity gets a little bit more negative. And then again, our velocity gets even more. And then for a little while here, we're moving at constant velocity. And then our velocity slows down some more. And then we get down the bottom, our velocity is 0 again. All right, let's see what the acceleration vector looks like. So we had 0 velocity, and now all of a sudden we have negative velocity. So our acceleration vector is going to be pointing downward because we're accelerating in the downward direction. When we get to this point here, our acceleration goes to 0 because remember, we said we're moving at constant velocity. And now here's where it gets interesting. You see we had a big downward velocity, and now all of a sudden our velocity is now smaller. So what direction is our acceleration going to be? Well, hopefully you guys realize the acceleration now is going to be upward. Okay, because the elevator is moving downward, but it's slowing. That means that the acceleration vector is going to be in the opposite direction of what the velocity vector is going. So we started off with an acceleration vector going downward, and we ended up with an acceleration vector going upward. But at every point, our velocity vectors were always pointing downward. Does this make sense to everybody? It's important that you understand this. Okay, so I see one person, I see 2 people were brave enough to say that they kind of sort of understand it, but apparently they're a little bit iffy on that. So think about it. And also remember that what we're doing right now is being recorded. And I am going to put this up on Canvas probably sometime tomorrow. And also remember that your book explains all this. So definitely read the book. I mean, sometimes the book explains things in ways that are different than I do. In fact, quite often the book explains it in ways that are different than I do. And sometimes my way of explaining it makes more sense to certain people, but other times my way of explaining it doesn't make as much sense as the book's way does. So it's good to see things from 2 different perspectives there. So listen to me, but also read the book. All right, so let's now go on to, let's do some problems. Up until now, you guys have not really had difficult homework problems. All of the math has been really, really easy. You know, you just multiply or add or subtract. You haven't really had a chance to show me how good you are at math. Well, today that changes. Today, you're going to get a chance to show me how good you are at math. All right, what you see on the screen right now are a bunch of equations that are known as the equations of motion. I like to refer to them as the Dr. Seuss equations because I made up this poster. I did not get this picture that you see here. This is not a picture that um, uh, that I drew myself, obviously. I mean, hopefully you guys recognize it. You guys, did you read Hop on Pop when you were kids? Remember in Hop on Pop, the Dr. Seuss book says up, pop, pup is up. All right. The reason that I like this drawing here is because by using the equations of motion, we will be able to figure out how high is the dog above the ground at any given time. These equations right here, this one and these others, these describe the motion of this dog as a function of time. Because remember last time we said that X is not going to be the independent variable. X is now the dependent variable. Time is now our independent variable. All right, so it is important for you guys to know where equations come from. In a few minutes, I am going to derive this equation, and I'm going to want you to take notes because you should know where equations come from. I don't like it when somebody says, well, here's an equation, and don't worry about where it comes from. Just take this equation, just use it, do the homework, life is good. No, 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 no. You need to know where the equation comes from. You shouldn't use an equation that you don't know where it comes from. But I'm not going to do that right this very minute because I don't want to get bogged down in the derivation. And so you get lost in the derivation and then you just kind of give up. So for the next few minutes, I'm going to do something that I hate doing. For the next few minutes, I'm going to say, let's just trust that these equations work. And let's use these equations to solve some problems like you're going to see in the homework tonight. And after we've done a few of those, then we're going to come back and we're going to find out where these equations come from. Because I think that's really important. That's what makes physics physics, is understanding where the equations come from. All right, but for right now, let's do something that's kind of against my religion, but I'm going to do it anyway. All right. Let's do a problem like you're going to see in the homework tonight. Let's say that we've got a car that starts off at, when t equals 0, this car is 12 meters away from the origin. And let's start off easy. Let's say that the initial velocity is 0. All right? Now, what's going to happen is the car is going to accelerate, and we're going to assume constant acceleration. So we're going to say that the car is going to accelerate at a rate of 2 meters per second per second. So I'm going to write that as a squared. And then I want to know what is x final when t equals, I don't know, let's say 5 seconds. All right. So there's a couple of ways we could do this. One way is we could just, kind of draw it out and try and, figure it out by brute strength. So we know that the initial velocity is 0. And then we know that it's going to accelerate so that at some point later, it's going to be moving kind of slowly. And then later it's going to be moving a little bit faster. And then later it's going to be moving faster still. And later it's moving faster still. So we could try and figure it out by doing the dot diagram, but let's just use the equation that we have decided works. Okay, so let's make a list of what are the things that we know and what are the things we don't know. So what I want to know is x final. That's the thing I don't know what is, and that's what I want to know. Okay, what are the things that I do know? Well, I know what the time is. I know what the initial position is, so let's call that x initial. So I know what that is. I know what the initial velocity is. All right. So let's make I need an equation that has an x final in it. And then all of these other things that are in the equation, I know what they are. So let's go back here temporarily to our previous thing. And okay. So let me clear out all these marks here. All right. So, well, let's look at this equation right here, the one in yellow. X final. So we see X initial, which we know, V initial, which we know, T, which we know, acceleration, which we know. Yeah, it looks like this is the equation that's going to do it for us. Everything over on the right side is stuff that we know. All right, so X naught plus V naught T plus 1/2 AT squared. All right, so let's go back over here to this other page. And I'm just going to go ahead and rewrite the equation. So X final equals X initial plus V initial T plus 1/2 AT squared. By the way, I do not expect you to memorize this equation. Physics is not about memorization. Physics is about understanding. So when we take our test, and by the way, we are going to be taking a test in a little bit less than 2 weeks now. So remind me to talk more about that in a couple minutes. But when we take the test, you can use what I call a cheat sheet, and you can have a piece of paper where you can write anything you want on this piece of paper. And in fact, you can even download my paper. You see this picture you see with the equations and the Dr. Seuss picture on there. If you look on Canvas, you will find out that I have posted this handout on Canvas. I've called it the Equations of Motion handout. If you want, you can just print this handout, print it out, and you can keep it right by your side while you're working on the homework. And you can also keep it by your side while you're working on the test. I do not expect you guys to memorize this. Okay, so if we know what X naught is, and I forgot what I said it was. Did I say 12? I think I said it was 12. The initial velocity I said was 0, so that makes it easy. So this guy, that whole term just goes away. That's nice. The acceleration, I think I said was 2 meters per second squared. And then the time, if I remember right, I think I said it was 5 seconds, right? And by the way, this is 12 meters. So X final then is equal to 12 meters plus 0 plus, so 1/2 times 2 times 5 squared. 1/2 times 2, that just goes away. 5 squared is 25. So 25 plus 12 is 37. So X final equals 37. And what units is that going to be? Well, this 12 is in meters, but what units is this guy in? We've got 5 squared. Well, 5 what? 5 seconds. So that's going to be seconds squared. And our acceleration here was measured in meters per second. So meters per second squared times second squared. Second squared on top, second squared on the bottom. We're left with meters. So we got 12 meters plus 25 meters is 37 meters. Okay, is that straightforward? In your homework tonight, they're gonna give you problems like this. All right, I'm seeing some yeses there. That's good. Okay, so the important thing is to look at these equations that we had on the previous page. Okay, and figure out which one of these equations is the one that you need to use to do the job. So sometimes there'll be problems where they tell you what X initial is, they tell you B initial, they tell you A, they tell you T. Other times, they may not tell you what T is, but they might ask you to find out the final velocity. Okay, so if they have an equation where they don't tell you what T is, then you have to use these other equations here. So it's up to you to figure out which one of these equations is the right equation to use. And so just, let's see how you do. Give it your best shot there. Let's do one other problem like you might see in a homework tonight. Okay. Let's suppose that they tell you that you're driving down the road and your initial velocity is 25 meters per second. And let's say that you hit the brakes and you come to a stop. So your final velocity is 0 meters per second. They don't tell you what time. They don't tell you how much time it took, but they do tell you how far you moved while you were slowing down. So let's suppose that they tell you that the car moved 63 meters, and they don't tell you what the initial position is, but let's assume that the initial position is 0, because remember how we said we can put the origin wherever we want? So let's say, here's a picture. So let's say the car is right here and is moving at 25 meters per second. And let's put that at our origin because it makes it a little easier to see. All right, so the car is going to be moving along, slowing down, stopping. So right here, here is where the velocity equals 0. And this distance in between the two is 63 meters. So we don't know how much time it took to do that, right? But I want to know what is our rate of acceleration. Or now you might say, well, in this case, we weren't accelerating, we were decelerating, we were slowing down. That's okay. Decelerating is just negative acceleration, right? So I want to know what my rate of acceleration is. All right, so what I've done is I've listed all the variables here, and you'll notice the thing that we want to know is A, but we don't know what T is. All right, so we need an equation that has an A in it, because if it doesn't have an A in it, it's not going to help us. And we need an equation that does not have a T in it. All right, so which equation can we use here? So let me write these down because I'm afraid when I go back, I might lose them. Okay, so let's go back to the previous page. And okay, now here, if I erase my screen right now, well, I guess I better because otherwise you're not going to be able to see anything. I need a better way to show this. All right. So remember what I said? I said that we are looking for acceleration. We don't know what time is. So I need an equation that has an A in it and does not have a T in it. Does anybody see? Oh, okay, good. Sam's way ahead of me. All right. So Sam is saying that the equation we need is probably this one right here. Because see, it's got an A in it, which is good. And it's got a V final, and we know what V final is, and we know what V initial is. And delta X, that's just, delta X is X final minus X initial. So we know both of those. Yeah, so I'm agreeing with Sam here. This equation is going to do it for us. All of the other equations are going to be a problem because the other equations, they have T's in them. And so if we don't know what A is and we also don't know what T is, then we got a problem. We got two unknowns and only one equation. But this equation down here, that's going to do it for us. Okay, so let's go back to the previous page. And unfortunately, I've had to erase all my notes here. So let me just make a list. So X initial, X final. And by the way, what I'm doing right now is what I recommend you do. I write down all of the variables that we might have to work with. Okay, so X initial, we defined that to be 0. X final, we were told was 63 meters. That's how far it took us to stop. V initial, we said was 25 meters per second. V final, we said was 0 because we came to a stop. The acceleration is what we're looking for, so I like to put a box around it just to remind us that's what we're looking for is the acceleration. And then T, we don't know, but we don't need to know because we found an equation that doesn't have a T in it. So it's okay if we don't know it. All right, so the equation we want is VF squared equals V naught squared plus 2A delta X. Now, where did I get that equation? I got it from the previous page. Okay, I got it from right, oh, I keep doing that. Okay, I got it from right here. I did not have to memorize it. I just got it off of that page. All right, so let's go back here. All right, so all we have to do now is just V final, we know is 0. Actually, let me switch to a different color here. Right. So V final we know is 0. I didn't mean to erase that. Okay. Right. No, V initial we knew was 25. The acceleration is what we're looking for. And delta x, that's just x final minus x initial. And since x initial is 0, we can leave that out. So what we got is Vf squared equals V naught squared plus 2a. Delta x is just going to be x final because x initial is 0. So from this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? How would we solve that for a? Well, let's try subtracting a v naught squared from each side. So that's going to give us vf squared minus v naught squared equals 2a x final. Okay, what are we going to do next? Well, let's divide by 2, and let's also divide by x final. They go away. And so what we're left then is a equals this. And now it's just plug and chug. So just take these numbers and plug them into here. And you get your answer. You guys see how this works? So if you're good at algebra, tonight's homework should be pretty simple. All right, so Sam is saying she got negative 4.96. I haven't worked out the math. Okay, so Taituan agrees. All right, good. All right, so in that case, I'm going to trust that you guys did it. All right, so if you do your homework like this, you should have no problem. Now, like I said before, I think it's really important that everybody knows where the equations come from. I don't, whoops, let's see, no, okay. So I want to derive the mother of all motion equations, okay? I think it's really important that we know where this equation comes from. Let's see, do we have enough time? Yeah, we do, we have enough time. All right, so what I'm about to do is I'm going to derive the equation, and I want you guys to realize that this is something that I think is very, very important. What makes physics physics is not taking some equation that we don't know where it came from and then just using it and getting an answer. Physics means figuring out where the equation came from. That's what makes physics physics. So Austin just asked if you need to write this down. Well, let me just say this. What I'm about to do might possibly be a question on the test that we're going to take in less than 2 weeks. Wink, wink, nudge, nudge. Okay. So Austin, I'll leave it up to you to decide whether or not you want to write it down. But one thing I will tell you is that I am recording this, and I am going to post the recording on Canvas. So if you want to just kind of watch and not worry too much about taking notes, but just kind of understand what's going on, and then come back later and watch the recording and get all the little details then, that would be okay. That would be all right. Okay, so I'm going to do this derivation now. So the way I'm going to do it is I'm going to start by just drawing a couple diagrams here. If I have acceleration equals 0, so that means I have constant velocity. Okay. If I were to make a graph of position as a function of time, and I have constant velocity, hopefully you guys are agreed that that graph is going to look something like this, right? Because the velocity is the slope of this line, and if it's constant, then it's a straight line. What if I were to draw a graph of the velocity as a function of time, and it's constant velocity? So what would that look like? Somebody want to unmute yourself or type it into the chat box? What would the graph look like if I have constant velocity And I want to know what the velocity looks like as a function of time. Very good. Horizontal line. That's exactly what it's going to be. Okay? Right. Now, remember the equation distance equals rate times time, which I prefer to write as x final equals velocity times t. That's the way that I prefer to write it. Okay? Well, if I take this graph of velocity versus time and I look at, I make it into a rectangle here, and I look at the area of this rectangle. What is the area of a rectangle? Well, area of a rectangle is height times width. What is the height of this rectangle? Well, the height of the rectangle is the velocity. What is the width of the rectangle? Well, that's the time. So now my V looks kind of like an R. Well, let me change that, make the V look more like a V. Okay. So are you guys agreed then that the area is equal to velocity times time, but if velocity times time is distance, what that means is that the area underneath my graph here of velocity versus time, that whatever area is down here, that area equals my distance. Do you guys will agree with me when I claim that? So I need to see some yeses or no. If I make a graph of velocity versus time, I'm going to get a horizontal line and the area underneath it will equal my distance. Okay, good. All right, so now if you believe that, then we're ready to take the next step. What if I'm accelerating? But it's going to be a constant acceleration. Okay. So the acceleration is not zero anymore, so my velocity is changing. All right. So if I make a graph of position as a function of time, right, you guys agree that it's going to look something like this? Because the slope right here, that's my velocity, and then the slope right here has changed. So you see how the slope is increasing? So I am accelerating. Okay. All right. So that's my graph of position versus time. But what if instead of doing that, let's make a graph of velocity versus time? Yeah, Calvin, that's fine. Don't worry. All right, so velocity versus time. All right. Now let's assume that we start off at some non-zero velocity. We don't have to start off at zero velocity. We can start off with some velocity that we call V naught that is not necessarily zero. And now if our acceleration is constant, that means our rate of change of velocity is going to be constant. So it means that if we're looking at velocity as a function of time, it's going to be a straight line. So after some amount of time has passed, we are now at a new velocity, V final. Okay, now here's the important thing. If it is true that the area under this curve equaled the distance before, then I will say that that's still true. Even though the velocity is not constant anymore, it's still true that the area under this curve equals the distance that we traveled. If you will let me get away with that, then the rest of this is going to be really easy. We can do this just using a little bit of algebra. Okay, so let me clear this to make room. All right, so I need to know the area under this curve here, or under this chart. Well, some of you might have the formula memorized for the area of a trapezoid, but I'm willing to bet that most of you don't. So let's take this trapezoid and break it up into two pieces. So we got a rectangle on the bottom and we got a triangle on the top. Well, area of a rectangle, that's easy. That's just height times width. Area of a triangle, well, that's easy too. That's just 1/2 base times height. So this distance right here, that's how much time it took. So that means the width of our rectangle is going to be t, and the base of our triangle is also going to be t. The height of our triangle, well, that's going to be v naught. Or I'm sorry, the height of our rectangle. Height of our rectangle is going to be v naught. The height of our triangle, now some of you might say the height of our triangle is v final, but hopefully you realize that's not the case. The height of the triangle is v final minus v initial. That's the height of our triangle. Okay, so if I can just figure out what these guys are and add them together, that will tell me the total area, and that will tell me the distance that we traveled during that amount of time. You good with that? Okay, so then let me just clear some space here. I wish there was an easier way to erase things on Zoom where I could keep part of my screen and just erase the other part, but not so. Okay, so the distance then, which is equal to the area, is going to equal the area of the rectangle, which is v naught times t, because that's height times width, v naught times t, plus the area of the triangle, which is 1/2 base times height, but my base is t, and my height is v final minus v initial. Okay. Are you good on that? I hope you guys are following. And like I said, if you're trying to take notes and you're having trouble keeping up because I'm going too fast, don't worry, because everything that I'm doing here is being recorded. Okay. So let me just make a little room here. All right, so now it's just an algebra exercise. So I'm going to start with the definition of acceleration. Hopefully you guys remember that the definition of acceleration is delta v over delta t, which is v final minus v initial over t. So that's acceleration, right? What if I take this and I multiply both sides by t? You see how that goes away? So when I do that, I get v final minus v initial is equal to at. Well, hey, here's v final minus v initial. So instead of calling it v final minus v initial, let's call it at. So that means that my distance is equal to v initial times t plus 1/2 times t times a times t, which is equal to v initial t plus 1/2 a t squared. That is my distance. You guys good on that? All right. So now let me just take the let me just take the final step here. I'm going to take this equation. I'm going to make myself a little bit of room here. I'm going to submit a request to Zoom that they make it easier to erase large portions of the screen. Okay. All right. So now, what I'm going to do is what hopefully is easy to understand. So if I want to know what is my x final, do you guys agree that that's going to equal to whatever my initial position was plus whatever distance I moved during the time interval that we had? So if the distance is that means x final equals x initial plus this, which is v naught t plus 1/2 at squared. There you go. That is the mother of all motion equations. Okay. So what we have just derived is a really, really, really important equation. It's this one right here, which I call the mother of all motion equations. We have now derived it. So we now know where this equation came from. So we can now use this equation with confidence, knowing that it is, it'll do the job for us. So I call this one the mother of all motion equations because all of these other motion equations, they can all be derived from this. If you know the mother, together with the definitions here, so everything that's in yellow, okay, these are definitions. This is the mother of all motion equations. So if you know them, then by combining these together, you can now derive all these other equations. So these other equations, these guys down here, I call these the daughters, the daughter equations. This one up here, I call this one the mother equation. And then these guys here, these are just the definitions of acceleration and velocity. Okay, so if you know the mother plus these definitions, it's possible to derive all these. Now, I'm not going to take the time to do that. Well, I don't think it'd be useful the use of our time. Okay, but it is possible to do. All right, in your homework tonight, your job is basically to figure out which equation you want. Sometimes the mother equation is the one that you're going to want. Other times, it's going to be one of the daughter equations that's going to be what you want. And so all you have to do is just figure out, which one's the right equation, and then do a little bit of algebra. And I'm trusting you guys are good at algebra. If you're not good at algebra, you will be, okay? You might not be good at algebra today, but I promise you, within a couple of weeks, you are going to be very good at algebra. I've had a lot of students tell me, they say, Mr. Hendricks, I learned more math from your physics class than I did from my math class. Well, my reply to that is that all we're doing in physics is we're just making it more clear. We're giving you a reason for why you needed to know the math, okay? And we're giving you practice. So hopefully I'm not teaching you any new math you didn't already know. I'm just giving you a chance to get really good at that math. Okay, so let's talk about tonight's homework. Here is your assignment for tonight. You'll notice that the assignment is from chapter 3. So first I want you to read the book. Every year I always get some students to say, well, I don't need to read the book. I looked at Mr. Hendricks's lecture, so it's good enough. No, read the book, okay? Read the book. And then I want you to do problems 1 through 11, but only the odd ones. So again, I'm being nice here because the odd ones, the answers are in the back of the book. So that way you can look back there and you can see whether or not you did them right. Okay, then after that, then I want you to do problem number 19 and number 21. And then after that, I want you to do problems 25 through 29, all of them, both the evens and the odds. Okay. All right. So you guys good with that? Good. All right. Now, do you notice what I wrote down here? I said, ask me about my 1 hour policy, and you will definitely like it. Okay, so here's the deal. I understand that I've given you a lot of homework. For many, if not most of you, it's probably going to take you more than 1 hour to do all these problems. Now, it is not my intention to give you hours and hours and hours of homework. That's not what I want to do. So my 1 hour policy is that if you have worked on the homework for 1 hour, and it was a good, honest hour, well, you weren't goofing off, but you were actually seriously working for 1 full hour, okay? At the end of that hour, if you're not done, then what you can do is you can submit the homework and just include a note saying, Mr. Hendricks, I spent an hour on it. And then I will give you 9 out of a possible 10 points, because homework assignments are always worth 10 points. So if you didn't finish it, but you spent 1 hour on it, I'll give you a 9 out of a 10, even though you might have only done half the problems. I'll still give you a 9 out of 10. Now, I won't give you a 10 out of 10. If you want to get a 10 out of 10, you got to do all of them. But if you send me a note saying, Mr. Hendricks, I spent an hour on it, I'll give you a 9 out of 10, okay? And this is going to be the policy on almost every assignment that we do. There may be one or two where I will change that. And if that's the case, I'll certainly tell you. But on almost all of the homework assignments, that's going to be my policy. All right, one other thing that you guys should know is that, today's Wednesday. So next time that we would theoretically meet would be Friday. But as you know by now, Ames doesn't meet on Zoom on Fridays. So now that doesn't mean that Friday is a day off. That means that Friday is an individual study day. So we are not going to meet again as a class until Tuesday of next week. So you've got a lot of time to do these problems. You got plenty of time. So you should be able to spend more than 1 hour doing these problems. I really would hope that you would. Okay, but anyway, what's going to happen on Friday? Well, Mr. Wilson has asked all of our teachers to standardize on a time where we will be on Zoom every Friday between 2:10 and 3:40. And hopefully that matches with what your other teachers have told you. So those are our Zoom hours. Therefore, if you work on the homework and you're having trouble, you're finding that there's a problem that you just can't get it and you need some help, well, meet me here on Zoom on Friday between 2:10 and 3:40, and we'll work on the problems together. Okay. Does anybody have any question about anything that we have covered here? Not seeing any comments. Okay, all right. Miriam wants to know how many points the midterm will be. It'll be worth 100 points. And by the way, let's talk about when the midterm is going to be, right? So my plan is we're going to spend today plus one other class session talking about chapter 3, and hopefully that'll be enough time. Then we'll spend one more class session after that just doing review. No new material, we'll just spend the whole class session just reviewing everything we've done so far. And then the next session after that, which by the way will be not next week, but the week after for you guys, it'll be Tuesday of the week after next. That's when the midterm exam is going to be. Any other questions? Not hearing any, not seeing any. Okay. All right. So we've only got 2 minutes left. So, well, let's just call it good then. Tell you what I'm going to do, same as before. I'm going to turn off the recording in a minute because I realize that some of you might have a question and you don't want to ask it because you know it's being recorded and you don't want to be embarrassed. So I'm going to turn off the recording and then you can ask your questions. And if you don't have any questions and you want to leave, you can just leave. But don't forget to type bye into the chat box before you leave, because I take roll both at the beginning of the period and also at the end of the period as well. So good. All right. So I have just now, oops, not yet.